Welcome to qnawire.
Okay, so we have got some cyclohexanes. I'm going to draw Me instead of CH3. It means the same thing. It means methyl, and CH3s are methyl groups. And the question is, are these identical? Are they enantiomers or are they diastereomers? And I drew the first one wrong. My apologies. Right. Okay. And yeah, I think you've got the right idea. These are diastereomers. How do we know? Because we have one or more stereocenters, and upon moving from one to the other, we can tell that they don't share the same stereochemistry at each carbon, but we can also tell that they're not mirror images immediately, because if they were mirror images, we should expect both of these stereochemical stereocenters to change, but only one of them changes. So yeah, diastereomers, correct. Okay. Okay, now we got a dash to methyl up there and a wedge to methyl down here. And then we have the opposite over here. A wedge to methyl up here and a dash to methyl down here. Oh, nope, we've got chlorines involved. CH3 and a wedge to chlorine. Now we've got a wedge to CH3, but a dash to chlorine. And then, yeah, your question was, are these identical enantiomers or diastereomers? Well, are they identical? If they were identical, there would be some manner that I could rotate this molecule, perhaps about that axis. And what would happen if I did that? Okay, the methyl would move to the bottom, but it would be pointing away. And the chlorine would move to the top, but it would be pointing towards us. Is this the same as that? No, definitely not, right? So the only real rotation that could move this methyl to the back, like it is over here, is also going to have the issue of moving the methyl down to the bottom carbon, right? Which isn't going to help us. So these are not, in fact, identical. Okay, and they are, in fact, enantiomers. And an easy way to see that might be instead to rotate about this bond, right? So suddenly I would have the following. I'm actually going to move this out of the way. And I'm going to redraw it after having rotated it 180 degrees about that bond, right? So now the carbon's going to be on the left and it's going to be pointing away from us. Sorry, the methyl. And the chlorine is going to move to the left but be pointing towards us. Okay, so these are in fact mirror images of each other, right? Which means they are enantiomers. And the other way to do that would be to describe or determine the absolute stereo configuration there and there, here and here, and ensure that we are sure that what was R is now S and what was S is now R. Okay, next one. Now we've got this. Okay. Okay. So are these enantiomers, diastereomers? Are the identical same molecule? These are in fact the same molecule. These are identical. How do I know this? They each contain a plane of symmetry, right? This is a plane of symmetry. This is a plane of symmetry. Same thing on the left, same thing on the right. And if we rotate about this plane of symmetry, say this one, we're going to end up with the same molecule that you have on the left there, right? This carbon will move, chlorine will move there, but it will be pointing back, and this chlorine will move up there, but it will be pointing back. If we rotate 180 degrees about the line that bisects these two carbons. One thing that can help with these is build a model if you have a model kit.